Tonight we're going to explore something that sounds simple, but turns out to be one of the most disorienting truths in all of science. Emptiness. You think you know what empty means. You've seen an empty room, an empty glass. Maybe you've looked out at a clear sky on a cloudless day and thought, nothing up there but air. You have an intuitive, confident sense of what it means for a space to contain nothing. Here's what most people never realize. The emptiness you've experienced on Earth, the emptiest place you've ever stood, the most vacant room you've ever walked through, is not even remotely close to empty. Not by any physical measure that matters. It's not even in the same category as empty. It's crowded, packed, almost incomprehensibly dense compared to what empty actually means. Because in space, emptiness reaches a degree that doesn't have a word in any human language adequate to describe it. A vacuum so complete, so total, so absolute, that matter itself becomes a strange exception, an anomaly, a brief local accident in a universe whose overwhelming default state is nothing. And by the time we're done tonight, you're going to understand exactly what that means. Not in the abstract way you've nodded along with before, in the way that lands somewhere deep and doesn't let go. Before we get started, if you love exploring the depths of space and the great unanswered questions of the universe as much as we do here, take a moment to like this video or subscribe to the channel. It's a simple action, but it helps this channel reach more curious minds, and it keeps this journey going. Now, let's begin. Let's start with what you think empty is. Right now, wherever you are, there is air around you. Billions upon billions of molecules in every cubic centimeter of the space your body occupies. Nitrogen, oxygen, argon, carbon dioxide, water vapor. At sea level, 1 cubic centimeter of the air around you, a space roughly the size of a sugar cube, contains approximately 27 billion molecules. That's 27 followed by 18 zeros. You breathe this in without thinking. It feels like nothing. We call it air, but we perceive it as absence. It's invisible. It offers almost no resistance to your hand moving through it. It has no taste or smell in ordinary conditions. Our bodies evolved so completely inside this dense molecular sea that we stopped registering it. We call the air nothing because our senses can't usefully detect it. Now go to the best vacuum chamber on Earth, the most advanced laboratory equipment humans have built. Physicists at facilities like the Large Hadron Collider or cutting-edge research universities have created vacuums of extraordinary quality. They can pump out nearly all the air, leaving chambers with pressures 10 trillion times lower than normal atmospheric pressure. These are genuinely impressive technical achievements. The molecules remaining in the best laboratory vacuum are so few and so far apart that you'd need to search for minutes before your hand passed through a single one. That sounds very empty. It's not even close to the emptiness of space. In the space between planets in our solar system, the density of matter drops to roughly 5 particles per cubic centimeter, lower than our best laboratory vacuums. In the space between star systems in the Milky Way, that drops again to about 1 particle per cubic centimeter, one single atom in a space the size of a sugar cube. And in the vast voids between galaxy clusters, the largest empty regions in the observable universe, the density falls to something like 1 atom per 10 cubic meters. 1 atom in a space the size of a large refrigerator. That's where the universe spends most of its volume. Not in stars, not in planets, not in the dense clouds of gas that make beautiful nebula photographs. In void, in near-perfect emptiness that makes our best laboratory vacuums look like thick soup. This is the reality of space, and your brain is not built to process it. Let's try to feel this rather than just know it, because knowing it intellectually is not the same as understanding what it means. When you look up at the night sky from a dark location and see thousands of stars, your brain processes them as a kind of ceiling, a dome of light above you. It feels populated, dense with stars. The Milky Way looks like a river of light crossing the sky. You look at it and think, there's a lot going on up there. But what you're actually seeing is a projection, a flat image produced by the collision of your two-dimensional retina with a three-dimensional universe. Every point of light you see is separated from every other point of light by distances so vast they collapse the imagination. The nearest star to our Sun is Proxima Centauri, roughly 4.24 light-years away. A light-year is about 5.9 trillion miles. So Proxima Centauri is approximately 25 trillion miles from where you're sitting. If you drew the solar system on a piece of paper, with the Sun as a dot the size of the period at the end of this sentence, and kept that scale, Proxima Centauri would be about 4.5 miles away from your piece of paper. And the space between them? Not empty in the way your living room is empty. Not empty in the way a parking lot at 3 in the morning is empty. Empty in the sense that if you flew a spacecraft from here to Proxima Centauri at the speed of light, the fastest anything in the universe can move, it would take 4 years. 4 years of traveling at 186,000 miles per second. And during those 4 years, you would almost certainly not pass through a single object larger than a dust grain. You would cross 25 trillion miles of essentially nothing. Now multiply that by the number of such gaps in the galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. They are distributed through a disk roughly 100,000 light-years across and a few thousand light-years thick. The average distance between stars in our neighborhood is about 5 light-years. If you could somehow freeze the Milky Way and fly through it in every direction, you would spend the overwhelming majority of your time in the gaps between stars. The stars themselves, enormous structures ranging from a few 100,000 to billions of miles across, would occupy a vanishingly small fraction of the total volume. Astronomers have calculated this. If you shrank every star in the Milky Way to the size of a grain of sand and kept the proportional distances intact, those grains of sand would be separated from each other by distances of hundreds of miles. The entire galaxy, with all its hundreds of billions of stars, would be like a few thousand grains of sand scattered across the continental United States with nothing between them. That's what the Milky Way actually is. Not a crowded river of light, a vast, almost inconceivably empty space in which very occasionally something solid exists. Now let's go to the scale between galaxies. Because if the inside of the Milky Way is startlingly empty, the space between galaxies is something else entirely. The Milky Way and the Andromeda Galaxy are about 2.5 million light-years apart. Between them, there's no significant amount of anything. A thin scattering of gas, perhaps 1 atom per cubic meter, and the occasional stray star that's been flung out of one galaxy or the other by gravitational interactions. No planets, no stellar nurseries, no clusters, just vast, silent, almost perfectly empty space. 2.5 million light-years of it. If you traveled from the Milky Way to Andromeda at the speed of light, it would take 2.5 million years. The entire lifespan of our species, from the emergence of Homo sapiens to this moment, is about 300,000 years. The distance to our nearest large galactic neighbor is more than 8 times the entire span of human existence, crossed at the maximum speed the laws of physics permit, through essentially nothing. Imagine you're in a spacecraft in the middle of that void, roughly 1.25 million light-years from the Milky Way, 1.25 million light-years from Andromeda. You look in one direction and see a faint smudge of light. The Milky Way, your home. 100 billion stars compressed by distance into something you could cover with your thumbnail. You look in the other direction and see another faint smudge. Andromeda. And in every other direction, for hundreds of thousands of light-years, nothing. No stars. No gas clouds bright enough to see with the naked eye. No reference points. Just an emptiness so total that the concept of direction itself starts to feel meaningless. There's no up or down. No nearby surface that reflects light and tells your eyes what orientation your body is in. You are in a space so empty that the word empty doesn't carry enough weight. And here's the thing that makes it worse. This is not an unusual place in the universe. The universe at its largest scales is mostly void. When cosmologists map the distribution of galaxies across billions of light-years, what emerges is a structure that looks something like a 3-dimensional spiderweb. Galaxies and galaxy clusters cluster along filaments, thin threads of matter stretched across the cosmos. And between those filaments are voids. Enormous, nearly spherical regions containing almost nothing. The Boötes Void, one of the largest known voids, is roughly 330 million light-years across. Inside it, the density of galaxies is nearly zero. A region of space 330 million light-years in diameter, about 0.27% of the observable universe's total diameter, containing almost nothing. If the Milky Way were inside the Boötes Void, we would not have discovered that other galaxies exist until the 1980s. The nearest galaxy to us would have been so far away that we'd have had no observational evidence of it until our telescopes reached modern levels of precision. That's how empty the voids are. That's what most of the universe's volume actually is. Now let's talk about what this emptiness means practically. What happens when you stand in it? What your body encounters? What your mind does? Your body is not designed for true vacuum. Not remotely. Everything about your physiology was shaped by an environment of dense molecular activity. Your lungs evolved to extract oxygen from air, but they do this by creating a pressure differential, expanding your chest to draw air in, compressing it to push it out. In a vacuum, there's no pressure differential to work with. There's no air to draw in. Your lungs would expand and keep expanding because the pressure inside them is higher than the pressure outside. The air already in your lungs would rush out. Within about 15 seconds, you'd lose consciousness from oxygen deprivation. Not from suffocation exactly, more like the light going out. But before that, something else would happen. The moisture on your tongue and in your eyes would begin to evaporate. In a vacuum, the boiling point of water drops dramatically. At pressures low enough, water boils at body temperature. The saliva in your mouth would actually bubble. This wouldn't be painful. You'd lose consciousness before discomfort became significant. But it would be strange. The liquids of your body trying to turn to gas because the pressure holding them liquid has gone. You would not explode. That's a persistent myth. The skin and connective tissue are strong enough to hold the body together. You'd swell somewhat as gases in your blood tried to expand, but you wouldn't rupture. You'd just stop working, very quickly, as the machinery of your biology seized up for lack of the medium it was built for. This is what true emptiness does to the thing we are. It doesn't accommodate us. It doesn't do anything to us out of hostility. It simply doesn't contain the conditions that make us possible. We are density-dependent organisms adrift in a universe that is almost entirely not dense. Let's go smaller now, because the emptiness of space doesn't stop at the scale of star systems and galaxies. It goes all the way down. The atoms that make up your body, every atom in your bones and blood and brain, are themselves almost entirely empty. This is a fact that physics established over a century ago, and that the human mind still hasn't fully absorbed. An atom consists of a nucleus surrounded by electrons. The nucleus contains protons and neutrons. If you took a hydrogen atom, the simplest atom, a single proton orbited by a single electron, and expanded it so that the nucleus was the size of a marble, roughly 1 centimeter across, the electron would orbit at a distance of about 1 kilometer. The atom is 1 centimeter of solid matter at its center, and 1 kilometer of emptiness extending in every direction to the cloud where the electron moves. The electron itself, at this scale, would be essentially a point, too small to see, moving through a volume of space 1 trillion times larger than the nucleus itself. Everything else, the entire interior of the atom, is nothing. This means that everything you think of as solid is almost entirely empty space. Your hand on the table itself, the floor, the building, the earth beneath it, all of it composed of atoms that are, by volume, empty to a degree that staggers the imagination. When your hand presses against a table, what's actually happening is that the electron clouds of the atoms in your hand are being repelled by the electron clouds of the atoms in the table. You don't actually touch anything in the sense of solid matter meeting solid matter. You meet the electromagnetic force that holds electron clouds apart. The sensation of touch is the sensation of that repulsion. Solid matter is electromagnetic force between small points of actual mass separated by vast, empty atomic interiors. You have never touched anything in your life, not in the way you think you have. Now hold both of these things at once. The universe at its largest scales is mostly void. Giant filaments of galaxies separated by vast empty bubbles hundreds of millions of light years across. Inside those galaxies, the stars are separated by distances of light years. Trillions of miles of near-perfect vacuum between each sun. Inside each star system, the planets are separated by hundreds of millions of miles of vacuum, and the planets themselves are tiny specks in that volume. And inside every piece of matter, every rock, every planet, every star, every body, the atoms are themselves almost entirely empty. Nuclei separated from their electrons by distances that, scaled up, would put the nearest solid structure a kilometer away. Emptiness is not an exception in this universe. Emptiness is the rule. From the scale of superclusters down to the scale of subatomic particles, the universe is almost entirely nothing. Matter, the stuff that stars and planets and people are made of, is an extraordinary rarity. A brief, local concentration of structure in a cosmos that has no obligation to contain any. When you press your fingers together right now and feel resistance, you're feeling the universe's most basic protest against its own default state. You are a small knot of electromagnetic repulsion, maintaining the illusion of solidity inside a universe that is, to a precision that beggars description, almost perfectly empty. That is what you are. That is what everything is. Let's think about what this means for space travel. Because when people imagine journeying to other stars or other galaxies, they often have a vague sense that they'll be traveling through something. through space, as if space is a medium, a substance, a fabric that has texture and presence. It doesn't. Not in any way your senses can register. Imagine a spacecraft launched from Earth today. We accelerate it to the fastest speed any human-made object has ever achieved, roughly the speed of Voyager 1 when it was flung past Jupiter, about 35,000 miles per hour. We aim it at Proxima Centauri, the nearest star. The spacecraft leaves Earth's atmosphere. It passes the Moon, then Mars, then the asteroid belt, that region popular imagination thinks of as a dense field of tumbling rocks. In reality, the asteroids in the belt are separated from each other by an average of nearly 1 million kilometers. Our spacecraft passes through the asteroid belt without coming within 1 million miles of anything solid. The rings of asteroids that look dense in every diagram are, in reality, a vast empty region in which rocks occasionally float. Past Jupiter, past Saturn, past Uranus and Neptune, beyond the orbit of Pluto, into the Kuiper Belt, where trans-Neptunian objects drift in cold darkness, separated by distances of millions of miles. Then, into the Oort cloud, the theorized shell of icy bodies at the edge of the solar system, beginning perhaps 2,000 AU from the Sun and extending to 100,000 AU. The Oort cloud contains trillions of objects, but the average distance between them is likely tens of millions of miles. Our spacecraft crosses all of this without encountering anything. Then it enters the space between star systems, the interstellar medium. Here, for the next roughly 75,000 years of travel at Voyager's speed, it will cross a region containing about 1 atom per cubic centimeter. Moving at 35,000 miles per hour, the spacecraft sweeps through about 2 trillion cubic kilometers of space per year. In that volume, at 1 atom per cubic centimeter, there are roughly 2 followed by 33 zeros atoms. That sounds like a lot, but these are individual atoms, hydrogen nuclei, protons, each one a point particle with a diameter of about 1 femtometer, 1 quadrillionth of a meter. The spacecraft would encounter some of them, and at low speeds the encounters are entirely harmless. These interactions are so minimal they don't meaningfully affect the spacecraft's trajectory, temperature, or structure. For 75,000 years, the spacecraft travels through essentially nothing. Then it approaches Proxima Centauri. The density of particles increases as it enters the stellar environment of another sun. The emptiness very slightly decreases, and even here, even within the Oort cloud equivalent of another star system, the overwhelming majority of the volume is nothing. If you compressed all the matter in the Milky Way galaxy, all 200 to 400 billion stars, all the gas clouds, all the dust, into a single sphere, and asked what fraction of the Milky Way's volume it would occupy, the answer would be a number so small that writing it would require a page of zeros after the decimal point. The galaxy is not matter floating in space. The galaxy is space, in which matter occasionally, locally, briefly exists. Here's where the emptiness stops being just a physical fact and starts becoming something stranger. The emptiness of the universe is not an accident. It's not a flaw or a failure of abundance. The emptiness is why anything exists at all. Go back 13.8 billion years to the early universe. In the first fractions of a second after the Big Bang, the universe was extraordinarily dense. Not in the comfortable sense. Every point of space was packed with energy and matter at temperatures and densities that physics can barely model. There was no emptiness, no separation, just an incomprehensibly hot, dense, uniform plasma filling all of space. And then it expanded. As the universe expanded, it cooled. As it cooled, matter condensed from energy. Quarks formed protons and neutrons. Protons and neutrons began to find each other. Hydrogen and helium formed. For the next 380,000 years, the universe was still too hot and dense for atoms to remain stable. It was an opaque plasma, light bouncing between charged particles in all directions. If you'd been there, which you couldn't have been, you wouldn't have been able to see anything. Then the universe cooled enough for electrons to bind to nuclei. Atoms formed. The universe became transparent, and the light that had been trapped in the plasma was released, streaming in all directions. We can still detect it. It's the cosmic microwave background, the afterglow of the Big Bang, now stretched by 13.8 billion years of cosmic expansion to microwave wavelengths. After that, the universe entered what cosmologists call the cosmic dark ages. There were no stars, no galaxies, just enormous clouds of hydrogen and helium gas slowly being pulled by gravity into denser regions. Those regions were the seeds of structure, and as gravity pulled matter together, something extraordinary happened. The empty regions got emptier. The dense regions got denser. Structure emerged from uniformity, not because something was added, but because gravity sorted matter into concentrations and voids. The same force that gives you weight was, over hundreds of millions of years, carving the cosmos into its current shape, threading galaxies along filaments, hollowing out voids between them. The emptiness of the voids isn't the absence of structure. It's the product of structure. The voids are empty, because the matter that could have been there was pulled away by gravity, attracted to the denser regions where galaxies form. The emptiness and the fullness are two sides of the same gravitational process. Without the emptiness, there would be no stars. Without vast volumes of low-density void, allowing gravity to work over large scales, matter couldn't have collapsed into the dense hot cores where nuclear fusion ignites. Every star you've ever seen, every star that has ever shone, exists because the universe had the good sense to be almost entirely empty everywhere else. The emptiness didn't prevent the universe from producing stars and planets and life. The emptiness is what made them possible. Let's think about what the emptiness does to light. Light, as you experience it on Earth, is visible because of what it bounces off. Sunlight fills a room because it reflects off the walls, the furniture, the floor, the particles of dust floating in the air. You see a shaft of light coming through a window because the photons in that shaft are bouncing off dust particles and reaching your eyes. The air itself scatters light. That's why the sky is blue, why sunsets are orange, why clouds are white. In space, none of this happens. A photon launched from the sun travels in a perfectly straight line at 186,000 miles per second until it hits something. If nothing is in its path, it keeps traveling. It doesn't illuminate the space around it. It doesn't scatter. It doesn't create the faint ambient glow you associate with a lit room. It is invisible until the moment it strikes a surface or enters an eye. This is why photographs from space probes like Voyager or New Horizons can show the blackness of interstellar space, even while being bathed in sunlight. The sunlight is there. The photons are there, streaming outward from the sun in every direction. But they're invisible, because there's nothing to scatter them, nothing to reflect them back into the camera. You can be in the full glare of the sun, in open space and look sideways and see nothing. Absolute blackness in every direction except directly toward the sun itself. Imagine standing on the hull of the Voyager 1 spacecraft right now. The sun is visible, a very bright point of light, far brighter than any star but small, distant, reduced by 165 AU of separation to a concentrated dot of brilliance. The light from that dot falls on the surface you're standing on. One side of you is brightly lit. The other side is in shadow, not dim shadow, not the soft shadow of a room with multiple light sources, but absolute shadow. Perfect black. The light is there. The photons are passing everywhere around you. But they're invisible. They only become visible at the moment they hit something solid. The emptiness doesn't just mean there's nothing there. It means the light that's everywhere is also effectively nowhere, because light without surfaces to interact with is light that might as well not exist, from your perspective. Now, let's consider the emptiness from an even stranger angle. We've talked about the emptiness between galaxies, the emptiness between stars, the emptiness inside atoms. But there's another layer of emptiness that modern physics has revealed, one that sits even deeper in the structure of reality. Inside the proton, the dense, solid nucleus of the hydrogen atom, the fundamental unit of what we call matter, there is more emptiness. Protons are not solid objects. They are made of quarks, 3 quarks, bound together by the strong nuclear force through the exchange of particles called gluons. But here's the thing. The quarks themselves account for only about 1% of the proton's mass. The remaining 99% comes from the energy of the gluon fields binding the quarks together, and from the constant churning of virtual quark-antiquark pairs popping in and out of existence in the quantum vacuum. The proton is not a solid billiard ball. It's a seething quantum system, mostly energy, containing 3 quarks that don't even sit still. They're in a constant state of quantum motion, their positions smeared across a probability distribution rather than fixed in place. And the quarks themselves, they appear, as far as current physics can determine, to be point particles. 0 size, no internal structure, mathematical points in space. So matter, at its deepest accessible level, is made of point particles embedded in quantum fields bound together by force carriers, the whole system generating mass not through substance but through energy and interaction. The solidity you feel, the hardness of a table, the resistance of a wall, is entirely a product of electromagnetic and nuclear forces operating between things that are themselves, at the deepest level, essentially geometry. The universe is not made of stuff. The universe is made of relationships between nearly nothing, playing out in almost nothing, across a backdrop of nothing. That is the deepest answer to what empty space really is. Let's slow down and just be in this for a moment. You're lying down right now, or sitting, or resting. Your body occupies a small volume of space. Inside your body, trillions of atoms are in constant motion, vibrating, bonding, reacting, signaling. Each of those atoms is almost entirely empty. The nuclei at their centers are separated from their electron clouds by proportional distances that would, scaled up, put the nearest structure a kilometer away. And the quarks inside those nuclei are, as far as physics knows, points. Below you, the Earth is 7,900 miles in diameter, composed of roughly 10 to the 50th power atoms, each one almost entirely empty. The solid planet beneath you is, at the level of the physics that actually describes it, a particular arrangement of forces acting between points of concentrated energy in a vast, empty quantum field. Above you, the atmosphere thins over the course of about 60 miles into the near vacuum of low Earth orbit. Above that, the Moon is 230 to 9,000 miles away. The Sun is 93 million miles away. The nearest star is 25 trillion miles away. Between all of these objects, the density of matter is lower than the best vacuum laboratory equipment on Earth can create. And beyond the stars of the Milky Way, separated by millions of light years of space, containing perhaps 1 atom per cubic meter, are other galaxies. Billions of them. Each one a concentration of matter so local, so brief on cosmic timescales, that from outside it would look like a faint smudge against the overwhelming blackness of void. This is the universe you live in. This is where you actually are. Not in a cozy, matter-filled cosmos where things are the normal state and gaps are the exception. In a vast, predominantly empty space in which matter, including you, including everything you've ever touched or loved or known, is the rarest, most improbable, most extraordinary exception. Now let's think about what this emptiness means for the question we almost never ask directly, but always carry with us. Are we alone? If you took the emptiness of the universe seriously, really seriously, the question of extraterrestrial life becomes simultaneously more urgent and more complicated. The universe is almost entirely empty. But that almost matters enormously. The residual matter that does exist is distributed across roughly 2 trillion galaxies, each containing hundreds of billions of stars, most of which likely have planets. The number of potentially habitable planets in the observable universe alone may be in the quintillions. Vast quantities of chemistry, of solar energy, of liquid water, of the conditions that allowed life to emerge on Earth, distributed across unimaginable distances. Life on Earth emerged in a specific location, in the ocean, probably near hydrothermal vents or in warm, shallow seas, under specific chemical conditions, at a specific point in the history of a specific planet orbiting a specific star. Those conditions exist because our solar system condensed from a particular cloud of gas and dust, enriched by earlier generations of stars that had lived and died. Our atoms were cooked in stellar interiors across billions of years before they became part of us. The same process happened everywhere. The same stellar nucleosynthesis that produced our carbon and oxygen and nitrogen produced those elements in every star that ever lived, in every galaxy in the observable universe. The elements of life are not rare. They're the most common complex products of stellar evolution. But the universe is so empty that even if life is common in principle, the distances between inhabited worlds, if they exist, may be so enormous that no signal, no spacecraft, no form of communication we can conceive of would ever bridge them in any meaningful time frame. Consider, even within our own galaxy, if there were 1 million inhabited planets, they'd be separated from each other by an average of roughly 300 light years. Communication at the speed of light would take 300 years per message. No conversation possible. Only broadcasts into the void, arriving centuries after they were sent. If intelligent civilizations exist at our cosmic address and are trying to reach us, their signals may already be here, passing through us. We simply haven't detected them. Or they haven't aimed at us. Or the signals have been stretched and faded by the emptiness into something below our detection threshold. The universe's emptiness doesn't just make space travel to other civilizations nearly impossible. It makes contact itself nearly impossible even at the speed of light. We are separated from any other intelligence that might exist not just by distance, but by time. The time it takes light to cross the empty gulf between us. We may be completely surrounded, at cosmic scales, by intelligent life, and utterly, practically alone. Let's bring this home in a different way. Most humans, most of the time, live as if the world is solid, as if matter is the normal state of things and emptiness is the exception. We build walls and floors and roads. We fill our spaces with objects. We navigate by surfaces and textures and resistances. The physical world tells us at every moment, things are here, things are real, things have presence. This is entirely correct for the scale at which we live. At the human scale, meters, kilometers, the distances our ancestors needed to navigate, matter is everywhere, and emptiness is rare. You cannot walk from your home to any useful destination without passing through many solid objects or surfaces. The human scale is the scale of matter. But zoom out, and the picture inverts completely. At planetary scales, most of a solar system is void. At galactic scales, most of a galaxy is void. At cosmic scales, most of the universe is void. And zoom in past the human scale to atomic dimensions, and the material you thought you were made of is itself mostly empty. The scale of matter in this universe is a narrow band, a particular range of sizes, roughly from atoms to galaxy clusters, where structure exists, where things touch, where force fields create the illusion of solidity. Above that range, emptiness. Below that range, emptiness. We live in the thin, improbable middle, surrounded on all sides, at every scale, by nothing. There's something clarifying about this, if you let it be. The things that fill your life, the objects and textures and encounters, the resistance of the world against your hands, the weight of your own body, all of it is force fields interacting across mostly empty space. The warmth of another person is energy radiating from matter that is itself almost entirely void. The sound of a voice is compression waves moving through a gas of molecules separated by distances millions of times their own diameter. Everything real is almost nothing. And yet, it is everything. You are, by the mathematics, almost entirely empty space. By the experience, you are entirely yourself. Both of these things are true simultaneously. The emptiness doesn't make you less real. It makes the fact that you are real, that matter organized itself into something capable of wondering about its own emptiness, more extraordinary than any description can capture. We talked about the emptiness between galaxies, between stars, between planets. And we went inside the atom and found that the atom itself is almost entirely empty. A nucleus the size of a marble, orbited by an electron a kilometer away at the scale we imagined. But what about inside the nucleus? What about the structure of the protons and neutrons themselves? What about the space between them? Not the space of astronomy, not the void between stars, but the emptiness that exists at scales a billion times smaller than an atom. And what about the fact that even in the most empty region of intergalactic space, quantum mechanics says the vacuum isn't empty at all? These are the questions that take the story from unsettling to genuinely strange. And by the time we're done tonight, the word empty will mean something to you that it didn't before. The nucleus of an atom is not a solid ball. It is not a dense, featureless lump of matter with clean edges and a definite surface. It is a cluster of protons and neutrons, particles called nucleons, held together by the strong nuclear force, one of the four fundamental forces of nature. and the most powerful force that operates at short range anywhere in the universe. The strong force is what holds the nucleus together, despite the fact that protons are all positively charged and electrical charge repels, like charges with a force that scales inversely with the square of distance. At the scales inside a nucleus, femtometers quadrillionths of a meter, protons are so close together that their mutual electrical repulsion is enormous. Without something stronger holding them in, every nucleus heavier than hydrogen would instantly fly apart. The strong force is stronger. It overcomes the electrical repulsion and binds nucleons together at these extremely short ranges. But it only operates at those ranges. It drops off so fast with distance that it has essentially no effect beyond the nucleus itself. This is why atoms don't all collapse into one giant nucleus. The strong force holds the nucleons together inside the nucleus, but doesn't reach out to affect the next atom over. Inside the nucleus, those nucleons are not touching in any ordinary sense. They're confined by the strong force into a volume roughly 100,000 times smaller than the atom itself. But even within that volume, they're not packed solid. They're in quantum states, probability distributions, rather than fixed positions. The nucleus has an interior structure, a quantum mechanical structure in which the nucleons occupy energy levels and move within the confines of the nuclear potential. And the nucleons themselves. Let's look inside a proton. A proton is made of quarks, 3 of them. 2 up quarks and 1 down quark, bound together by gluons, the carrier particles of the strong force. The quarks are not sitting still inside the proton, arranged at fixed positions like marbles in a bag. They're in a constant state of quantum motion. Their positions described by probability distributions, not coordinates. The gluons exchanged between them are themselves continuously appearing and vanishing. The quantum vacuum between the quarks is seething, with virtual quark-antiquark pairs popping into and out of existence on timescales so short they evade direct detection. The quarks themselves, the actual fundamental constituents of the proton, are, as far as every experiment ever conducted can determine, point particles, 0 size, not tiny spheres, mathematical points. The mass of a proton is about 938 million electron volts. The combined mass of its 3 constituent quarks is only about 9 million electron volts, less than 1% of the proton's total mass. Where does the other 99% come from? From the energy of the gluon fields, from the kinetic energy of the quarks in their constant quantum motion, from the continuous creation and annihilation of virtual particles in the quantum vacuum inside the proton. The proton's mass, the thing that gives matter its weight, that makes you heavy, that causes gravity to hold you to the Earth, is almost entirely not in the quarks. It's in the fields and the vacuum and the motion. It's in the emptiness between the point particles that actually constitute the matter. Your mass, almost entirely, comes from quantum vacuum energy inside protons and neutrons. You are not heavy because you're full of stuff. You are heavy because the empty space inside your atoms is energetically expensive to maintain. Now let's talk about what happens when you try to remove everything from a region of space. When you try to create a true vacuum, a space containing nothing at all. In classical physics, the physics of Newton, the physics of your intuition, empty space is just that. Empty. Remove the matter and the energy, and what's left is an absence. A geometric container with no contents. Vacuum. Quantum mechanics says otherwise. Quantum field theory, the most precisely tested framework in the history of science, accurate to more decimal places than any other theory ever developed, tells us that space is not a passive container. Space is itself filled with quantum fields. Every particle we know of is an excitation of a corresponding quantum field that permeates all of space. The electron field, the quark fields, the electromagnetic field, the Higgs field. These fields are everywhere, at every point in space, at all times. In their lowest energy state, the ground state, the closest thing to empty, these fields are not zero. They fluctuate, randomly, constantly, inherently. This is not a limitation of measurement. It's not uncertainty about what's really happening. It's what's really happening. The quantum fields that fill all of space can never be completely still because of the Heisenberg uncertainty principle, which says that the more precisely you know one property of a system, the less precisely you can know the complementary property. For a field, knowing that it is exactly zero energy everywhere would violate the uncertainty principle. So it can never have exactly zero energy everywhere. The result is what physicists call the quantum vacuum, the lowest energy state of all the quantum fields simultaneously. And this state is not nothing. It is a seething, churning, fluctuating sea of activity. In the quantum vacuum, particle-antiparticle pairs appear spontaneously from the energy of the fluctuations, exist for an unimaginably brief moment, constrained by the uncertainty principle to be briefer the more energetic they are, and then annihilate back into the vacuum. These are called virtual particles, and the name is somewhat misleading because they are not simply hypothetical. Their effects are real and measurable. The Casimir effect is one demonstration. Take two perfectly flat, electrically neutral metal plates and bring them very close together in a vacuum. Between the plates, the range of virtual particles that can appear is restricted. Only fluctuations with wavelengths that fit between the plates are permitted. Outside the plates, all fluctuations are permitted. This imbalance creates a pressure difference. The vacuum pushes the plates together. This force has been measured. It is real. The quantum vacuum is pushing on things. The Lamb shift is another demonstration. A tiny but measurable difference in the energy levels of hydrogen electrons caused by the interaction of the electron with virtual particles in the surrounding quantum vacuum. This shift was one of the first precise predictions of quantum electrodynamics, and its measurement in 1947 was a landmark confirmation of the theory. The quantum vacuum is not nothing. In the deepest, most perfect void that physics can conceive of, far from any matter, far from any radiation, in the space between galaxy clusters in the largest voids in the observable universe. The quantum fields are still there, still fluctuating, still giving birth to and absorbing virtual particles on timescales too short to observe directly, but long enough to affect everything around them. True emptiness, a complete absence of everything, including quantum fields, is not just hard to achieve. It may be physically impossible. The universe, down to its deepest substrate, will not hold still. Here's something that will reframe everything we've talked about. We've been discussing the observable universe, the matter we can see, stars, gas, dust, planets, galaxies, the stuff that interacts with light, the stuff our instruments detect, the matter that makes up everything visible. This matter, the protons and neutrons and electrons that constitute stars and planets, and you, makes up approximately 5% of the universe's total energy content. 5%. The other 95% is something we cannot see, cannot directly detect, and do not fully understand. About 27% of the universe is dark matter. Dark matter doesn't emit light. doesn't absorb light, doesn't reflect light. It doesn't interact with electromagnetic radiation of any wavelength. Ordinary matter, the stuff you're made of, interacts with photons constantly. Electrons absorb and emit photons. Nuclei scatter photons. The entire rich variety of chemistry and spectroscopy, and the fact that you can see anything at all, depends on ordinary matter's willingness to interact with electromagnetic radiation. Dark matter doesn't do any of that. It exists in the same space as ordinary matter and doesn't affect the light passing through it at all. What it does do is respond to gravity. And what that means is that even when we look at the vast empty voids between galaxies, those regions that appear to contain almost nothing, 1 atom per cubic meter of hydrogen gas, the voids are not actually empty. They're threaded with dark matter, invisible, undetectable by any current instrument except through its gravitational influence. Present throughout the voids, but concentrated especially in halos, around galaxies and in filaments along the cosmic web. We know dark matter exists because of what it does to visible matter. Galaxies spin too fast. The stars in the outer regions of spiral galaxies move around the galactic center at speeds that cannot be explained by the gravitational pull of the visible matter alone. If galaxies contained only the matter we can see, stars in their outer regions should orbit more slowly, just as the outer planets of the solar system orbit more slowly than the inner ones. They don't. They orbit at roughly constant speeds regardless of their distance from the center. Something invisible is providing additional gravitational pull. That something is dark matter, forming vast halos extending far beyond the visible disk of every galaxy. Galaxy clusters bend light. When we observe very distant objects through galaxy clusters, their light is bent and distorted by gravity, a phenomenon called gravitational lensing. The amount of bending tells us how much mass the cluster contains. Without exception, galaxy clusters contain far more gravitational mass than their visible matter can account for. The invisible mass, dark matter, typically outweighs the visible matter by a factor of 5 to 10. The bullet cluster is the most striking example. 2 galaxy clusters that have passed through each other. The hot gas, the most abundant form of ordinary matter in clusters detectable in X-rays, was slowed by electromagnetic interactions during the passage. But the dark matter, which doesn't interact electromagnetically, passed through unimpeded. The result is a separation. The dark matter halos of the 2 clusters have sailed through each other and are now offset from the visible gas. We can map the dark matter through gravitational lensing. We can map the gas through X-ray emission. They're in different places. The dark matter went straight through because nothing stops it. This tells us something extraordinary about the emptiness of space. When you look at the vast intergalactic void and think you're seeing empty space, you're partly right. The ordinary matter density is close to nothing. But the space is also filled with dark matter, distributed in a web of invisible structure that shaped the cosmos. The galaxies formed where they did because dark matter halos formed first, providing the gravitational seeds that attracted ordinary matter and triggered star formation. The visible universe, the one you see when you look up at the sky, is a tracing of structure that exists primarily in dark matter. The stars and galaxies and nebulae are lit-up decorations on an invisible scaffold. The real skeleton of the universe is dark, unlit, invisible from the inside. The emptiness we perceive is real. Ordinary matter is genuinely sparse everywhere we look. But overlaid on that ordinary emptiness is an invisible structure we can only detect by its effects. The void is full of something. We just can't see it. We don't know what it is. Now let's talk about the remaining 68%. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that earned the Nobel Prize in Physics in 2011. The discovery was this: the expansion of the universe is accelerating. This should not be happening. After the Big Bang, the universe began expanding. Everything made sense. The expansion was driven by the energy of the initial event. But gravity, the mutual attraction of all matter for all other matter, should be slowing that expansion down. Over time, the expansion should decelerate. Eventually, if there was enough matter, it might reverse into a collapse. The supernovae measurements showed the opposite. The expansion is not slowing, it's speeding up. The distant galaxies are receding from us, faster now than they were in the past. Something is pushing the universe apart. Something is overwhelming gravity at the largest scales and causing the space between galaxy clusters to grow faster and faster. This something was given the name dark energy. It is not a substance in the usual sense. It appears to be a property of space itself, an energy density inherent to the vacuum, present in every cubic meter of empty space everywhere in the universe. Einstein called something like it the cosmological constant. He introduced it into his equations of general relativity to produce a static universe before Hubble discovered the expansion, and later called it his greatest blunder. It turns out he was right in a way he didn't intend. There is something like a cosmological constant, but rather than holding the universe static, it's driving an accelerating expansion. Here's the deeply strange thing about dark energy. It doesn't dilute as the universe expands. Ordinary matter. As the universe gets larger, the same amount of matter is spread through a larger volume, so the density decreases. Dark matter does the same. But dark energy appears to be a constant energy density of space itself. As space expands, creating new space, that new space comes with the same dark energy density as the old space. The total amount of dark energy in the universe is increasing as the universe grows. This means dark energy becomes more dominant over time, as ordinary matter and dark matter thin out with expansion, while dark energy stays constant or grows. The universe is not just expanding, it's expanding in a way that will become increasingly dominated by the expansion itself. The consequences are staggering. The galaxies we can see today, the roughly 2 trillion galaxies in the observable universe, are already mostly unreachable. The expansion of space means distant galaxies are receding from us faster than we could ever travel to them, even in a spacecraft moving at the speed of light. The observable universe has a horizon, a boundary beyond which light can never reach us, because the space between us and those distant galaxies is expanding faster than light can cross it. In roughly 150 billion years, every galaxy outside our local group, the small cluster of galaxies that includes the Milky Way, Andromeda, and a few dozen dwarf galaxies, will have receded past that horizon. Their light will never reach us again. The night sky will contain only the stars of our own local galactic merger, the eventual collision and combination of the Milky Way and Andromeda, and nothing else. Everything beyond it will be gone from our universe. Not destroyed, still existing, but permanently unreachable, their light redshifted to invisibility. The space between us expanding faster than communication can cross. The universe is not just empty, it is becoming more isolated. The islands of matter are drifting apart in a sea of expanding dark energy, and the sea is winning. The emptiness is growing. We need to zoom all the way out now. not to understand emptiness at the scale of atoms, not at the scale of star systems, not even at the scale of galaxies, but at the largest scale at which structure in the universe exists. What you find there is one of the most beautiful and disturbing images in all of science. Cosmologists call it the cosmic web. When you map the positions of galaxies across hundreds of millions of light years, what emerges is not a random scatter. It is structure, three-dimensional structure of extraordinary complexity and scale. Galaxies cluster along filaments, vast threads of matter stretching across hundreds of millions of light years. And those filaments intersect at nodes where galaxy superclusters form, the most massive bound structures in the universe. Our own galaxy, the Milky Way, sits in a supercluster called Laniakea, a structure discovered and mapped in full only in 2014. Laniakea contains the mass of roughly 100 million billion suns, spread across a region about 520 million light-years in diameter. 500 million light-years across. Our entire observable bubble of the universe, 93 billion light-years in diameter, contains something on the order of 10 million such superclusters. Between the filaments and the nodes, between the threads of the cosmic web, are the voids, the supervoids. These are regions of space where the density of matter falls to a tiny fraction of the cosmic average. Not just empty in the sense of no stars nearby, empty in the sense that galaxies themselves are rare. The largest voids are hundreds of millions of light-years across. Some may be over 1 billion light-years in diameter. Regions of space larger than the distance light has traveled since the first stars formed, containing almost no galaxies. The Boötes Void is one of the better-known examples. Discovered in 1981 by Robert Kirshner and colleagues, it spans roughly 330 million light-years. When first described, it was so anomalously empty that one astronomer joked that if the Milky Way were located inside it, humanity would not have discovered the existence of other galaxies until the 1980s, because the nearest galaxy would have been so distant that our telescopes wouldn't have resolved it until modern times. The cold spot, a region of the cosmic microwave background radiation that is slightly colder than its surroundings, may correspond to a supervoid even larger than the Boötes Void, potentially 1 billion light-years across. If so, it would be the largest single structure, or rather, the largest single absence, ever identified in the universe. A hole in the distribution of matter, 1 billion light-years in diameter. Stand back and look at the cosmic web as a whole. The filaments, the places where matter is, form a pattern that has been compared to a neural network, to mycelium, to the structure of the universe's own brain, if the universe had one. The filaments branch and reconnect. The nodes where they intersect glow with the light of galaxy clusters. The voids between them are dark and vast and largely silent. The ratio of void to filament in the cosmic web is roughly 80 to 20. Approximately 80% of the universe's volume is in the voids. Approximately 20% is in the filaments and sheets and nodes where galaxies live. The 80% is where almost nothing is. We live in the 20%. And even the 20% is mostly empty. The stars and the filaments are separated by light-years of vacuum. And the atoms in those stars are mostly empty space. And the nuclei in those atoms are themselves quantum systems of point particles separated by vast relative distances. Empty all the way down. Empty at every scale. From the supervoid spanning 1 billion light-years to the interior of a proton spanning a femtometer. The universe is overwhelmingly, comprehensively, at every level of its structure. Nothing. All of this is physics. But physics only tells half the story. The other half is what happens to a mind when it genuinely confronts the emptiness. Not when it reads about it or nods along to a video, but when it feels it directly. Astronauts have described this. The ones who have been far enough from Earth or oriented themselves in the right direction on a spacewalk to experience something approaching the true void. The International Space Station orbits at about 250 miles altitude. From there, Earth fills a large portion of the view. The planet is enormous, detailed, alive with color and weather. Astronauts describe looking at Earth from the ISS as profoundly connecting, seeing your home from outside, watching it turn beneath you, seeing the lights of cities at night and the blues of oceans in daylight, creates what's called the overview effect. The sudden visceral understanding that Earth is one small, fragile, interconnected thing. But some astronauts describe a different experience. The experience of turning away from Earth. Of looking not toward the planet but away from it, into the direction of open space. What they see, away from the reflective surface of Earth and the blazing sun, is black. Not a soft atmospheric black, a space black, an absolute termination of information. Your eye sends signals to your visual cortex, and your visual cortex has nothing to work with. Ed White, the first American to walk in space in 1965, described looking away from Earth and the sun and feeling a falling sensation. The vestibular system confused by the complete absence of visual reference, in a state of weightlessness. No up, no down, no sense of scale, no horizon. Nothing for the brain's spatial orientation systems to anchor to. Later, astronauts on Apollo missions described the experience of being on the far side of the moon, the first humans to pass behind another world and lose sight of Earth entirely. For roughly 45 minutes each orbit, the moon blocks Earth, blocks the sun, and the astronauts are in a radio blackout, unable to communicate with anyone. Frank Borman, Jim Lovell, and William Anders on Apollo 8 were the first to experience this. They described looking out the window during the far side passage and seeing a blackness different from anything they knew. A blackness that had no depth, because depth requires something at different distances, and there was nothing at any distance. The Apollo lunar module pilots who stayed in orbit while their crewmates walked on the moon were, for brief periods, the most isolated human beings in history. Mike Collins during Apollo 11 passed behind the moon, while Neil Armstrong and Buzz Aldrin were on the surface. For those intervals, Collins was more than 2,000 miles from the nearest humans, completely out of radio contact with Earth, alone in a spacecraft orbiting another world. Collins later wrote that he did not feel lonely during those passages. He felt, he said, aware of the size of the universe in a way that couldn't be manufactured. The darkness wasn't oppressive to him. It was, he wrote, serene. But it was the serenity of confronting something that had no opinion about whether he existed. A serenity that required you to bring something to it yourself, because the emptiness offered nothing. That distinction matters. The emptiness of space doesn't care about you. This is not hostility. The darkness does not wish you harm. The vacuum does not want to kill you. The void doesn't have preferences. It simply is what it is, indifferent in the most complete sense possible. Not the indifference of a person who has decided not to care. The indifference of a state of the universe that has no mechanism by which care could even be defined. For some people, this is terrifying. The feeling of being somewhere that has no record of your existence, no provision for your survival, no acknowledgement of your presence. For others, it's the opposite, a relief. If the universe is indifferent, then the weight of significance you've been carrying, the sense that everything matters enormously, that you are being observed and evaluated and found lacking, dissolves. The emptiness doesn't judge you, doesn't remember your mistakes, doesn't care what you accomplished or didn't. It's just there. It was there before you. It'll be there after. Both responses are the mind doing what minds do, reaching into the void for meaning, then calibrating to what the void actually offers, which is the physics, the mathematics, the structure, the cold and beautiful fact of almost nothing, organized by gravity and quantum mechanics into the brief, local, improbable thing that includes stars and planets, and people who wonder about the emptiness they're made of. Let's think about what happens to the human mind when the emptiness is not a spacewalk or an orbital flight, but months of continuous exposure. A mission to Mars takes roughly 6 to 9 months, with current or near-future propulsion technology. 6 to 9 months of traveling through the solar system's interplanetary medium. The sun shrinking. The planets no longer recognizable in the sky as distinct disks. Earth receding to a point, then to a dot. Then, for some of the journey, becoming invisible to the naked eye. What's outside the window for those 6 to 9 months is not the dramatic space of science fiction, punctuated by nebulae and alien worlds in the light of close stars. It's the same view, day after day. Stars that don't move. A slowly brightening or dimming point that is Mars. The sun, smaller than you've ever seen it. And the window itself, reflecting back the interior of the spacecraft more than it shows you the outside. Because the spacecraft is lit, and the outside is dark, and the contrast makes the darkness outside the window more absolute. Psychological studies of analog environments, Antarctic winter overstations, nuclear submarines, isolated research outposts, consistently identify a phenomenon called the third quarter effect. After roughly 3/4 of an isolated mission, depression and interpersonal conflict reach their peak. The novelty of the early mission has worn off. The end is in sight, but not close enough to provide motivation. The middle has become routine, but the routine is not comfortable. It's a routine of sensory monotony in a confined space, surrounded by a void. On a Mars mission, this peak would arrive roughly 4 to 5 months in. The crew would be somewhere between Earth and Mars, Earth invisible or nearly so. Mars still a dot in the forward view, surrounded by the same black window it's been for months. Astronauts selected for long-duration missions are chosen partly for psychological resilience, for the ability to generate internal meaning when the external environment provides none. The emptiness is the test, not the radiation, not the microgravity, not the engineering risk, though all of those are real. The test is whether the human mind can sustain itself in an environment that is, in terms of sensory richness and variety, about as close to nothing as it's possible to get while still alive. The remedies are social and cognitive, not physical. Crew cohesion, the quality of the relationships inside the spacecraft, consistently predicts mission psychological outcomes better than individual resilience scores. A crew that trusts each other and can talk openly does better in emptiness than a crew of individually resilient people who don't connect. Regular structured activities matter. Not just work tasks, but the creation of deliberate rhythm. Meal times together, recreation, Communication with Earth even when the delay makes real conversation impossible. Small celebrations of milestones. The human brain uses temporal structure to anchor itself when spatial structure is absent. When there's nothing to see and nowhere to go, time becomes the geography. The schedule becomes the landscape. And sleep is, in a way, how the brain rehearses emptiness and survives it. Every night, you voluntarily go dark. You release your grip on consciousness, on sensory processing, on the maintenance of the self. For 6 to 8 hours, you are in a state not entirely unlike the state that would terrify you in waking space, unresponsive to the environment, adrift in internally generated imagery, cut off from the external world. We've been practicing the emptiness our whole lives. Every night. We've just never framed it that way. We need to talk about where all this is going. We established earlier that dark energy is causing the universe to expand at an accelerating rate. That, in roughly 150 billion years, everything outside our local group will have receded past the cosmic horizon, invisible forever. What comes after that is the long, slow story of matter dissolving into the emptiness, without new material flowing into the Milky Way. Andromeda merger from outside, because everything outside is receding beyond reach. Star formation will gradually slow as gas is consumed. The most massive stars burn out first, in millions of years. Stars like the Sun last for billions. The smallest, reddest stars, red dwarfs, can persist for trillions of years, burning slowly and carefully on their meager fuel supplies. In roughly 100 trillion years, 10,000 times the current age of the universe, the last red dwarf will exhaust its hydrogen. The universe will contain no more burning stars, only stellar remnants, white dwarfs cooling over inconceivable timescales toward absolute zero, neutron stars spinning down to stillness, black holes growing slowly by absorbing whatever drifts within their reach. The universe will be dark, not the vivid dark of interstellar space with its backdrop of distant galaxies. The dark of a galaxy that has no burning stars, of a cosmos in which no light is being produced, of a void in which matter still exists but nothing is happening to it that produces radiation our eyes could see. And then, over even longer timescales, the remnants themselves dissolve. Proton decay, a process predicted by many grand unified theories of particle physics, though not yet observed, would, if it occurs, disintegrate ordinary matter on timescales of at least 10 to the 34th years. 1, followed by 34 zeros. Every proton, every neutron, every atom, in every white dwarf and neutron star and cold planetary body drifting in the dark, would eventually disintegrate into leptons and photons. The solids would dissolve into radiation. Matter itself would become emptiness. The black holes would last longest. Stephen Hawking demonstrated in 1974 that black holes are not permanent. Due to quantum effects near the event horizon, the same quantum vacuum fluctuations we discussed earlier, black holes slowly radiate energy. Particle-antiparticle pairs forming near the event horizon result in one particle escaping while the other falls in, slowly draining the black hole's mass. For a stellar mass black hole, this process takes roughly 10 to the 67th years to complete. For a supermassive black hole like the one at the center of a large galaxy, 10 to the 100th years or more. Numbers so large that they have no analogy in anything you have ever experienced or imagined. But given enough time, and time in the universe's far future will be abundant, Even the supermassive black holes will finish evaporating. The last, Hawking radiation, will disperse into the expanding void. And then there will be nothing left of the matter that once made stars and planets and people, except a diffuse haze of photons and electrons and positrons, too sparse ever to interact again, expanding forever through an ever larger void at temperatures indistinguishable from absolute zero. This is the heat death of the universe. Maximum entropy. No energy gradients anywhere. Nothing happening. Nothing able to happen. Not darkness in the sense we experience it, because darkness is defined relative to light, and there will be no light. Just an infinite, cold, diffuse emptiness in which the quantum fields still fluctuate, but their fluctuations cannot produce anything organized enough to matter. The universe began as a hot, dense, near-uniform sea of energy. It will end as a cold, vast, near-uniform sea of nothing. What happened in between? The stars, the galaxies, the planets. The 13.8 billion years of structure and complexity, the chemistry, the biology, the civilization, the moment you're having right now, listening to this, breathing, thinking, is the interesting part. The brief, improbable local exception in the long story of emptiness returning to emptiness. We are the middle. Here's the question that physics hasn't answered. We've established that quantum fields fill all of space, that the vacuum is not empty in any strict sense, that virtual particles and quantum fluctuations are the default state of space even in the deepest void. That dark matter and dark energy fill the universe with invisible stuff our instruments can barely characterize. So is true emptiness, a genuine, absolute nothing, a region of space devoid of any field, any energy, any structure, even physically possible. The honest answer is, we don't know. The vacuum of quantum field theory still has structure. The fields are there. The cosmological constant gives even empty space an energy density. Space-time itself, the four-dimensional fabric described by general relativity, has geometry, curvature, topology. Even the absence of matter doesn't remove the geometry of space-time, which can be curved by the presence of matter elsewhere, can carry gravitational waves, can expand or contract. Whether a true nothing, no fields, no geometry, no space-time, could exist or has any meaning, is a question that sits at the boundary of physics and philosophy. Some physicists argue that the universe began from nothing in a quantum fluctuation, that the laws of quantum mechanics permit the spontaneous emergence of a universe from a state of true nothingness. Others argue that this misunderstands the question, because quantum fluctuations require quantum fields, which require space and time to exist in. And if you have space and time, you already have something. The universe may be incapable of being nothing. The rules of physics may require that wherever space and time exist, energy exists too. At minimum, the vacuum energy of quantum fields. The baseline, the irreducible minimum, may be the quantum vacuum we described. Fluctuating, restless, never quite still. True emptiness may be forbidden. The universe, at its deepest level, may refuse to be nothing. This is either the most comforting or the most unsettling conclusion in all of physics, depending on how you come to it. The comforting reading: even in the deepest void, the most remote intergalactic space, the longest stretches between particles, the universe is still there, still doing something, still refusing absolute stillness. The unsettling reading: there is no rest in this universe, no stopping, Not even in the vacuum. The vacuum itself is in perpetual motion. Quantum fields fluctuating at every point in space for the entire life of the universe and beyond. Churning in the dark even when every star has died and every black hole has evaporated and no organized structure of any kind remains. Forever. Let's pull back to here, to now. We've spent this entire journey moving through scales of emptiness. From the vacuum between galaxies to the void between stars, to the near-nothingness of the interplanetary medium, to the emptiness inside atoms, to the quantum vacuum inside protons, to the fact that, even true, nothingness may not be achievable. What does it all mean? For physics, it means that matter, the solid, substantial, weight-bearing stuff that your everyday life is entirely built on, is an extraordinarily thin local exception to the near-universal rule of emptiness. The protons and neutrons and electrons that make up you and the chair you're sitting on and the planet beneath your feet represent about 5% of the universe's total energy content, distributed in concentrations so local and so brief on cosmic timescales that they barely register in the full accounting. For biology, it means that life, the organization of matter into systems capable of self-replication and metabolism, and eventually awareness, is more improbable than the word improbable can carry. Not just because the conditions required are rare, because the matter required is rare. Because the universe has no obligation to contain matter at all. That it does, and that some of that matter organized itself into DNA and nervous systems and creatures that look up at the emptiness and wonder about it, is not something the universe required. It's something that happened anyway. For you, sitting here tonight, it means something quieter and stranger. You are almost entirely nothing. The atoms that compose you are almost entirely empty. The electrons orbiting in those atoms exist as probability distributions rather than points. The quarks inside the nuclei are quantum smears of possibility. The fields that make those quarks real are fluctuations in a vacuum that permeates all of space. You are, in the most rigorous physical accounting, an extraordinarily organized pattern of empty space that happens to be self-sustaining and self-aware. And that pattern, that brief, local, improbable organization of almost nothing into something, is capable of sitting in a warm room on a small planet orbiting a middle-aged star in the outer arm of a spiral galaxy, and knowing it's surrounded by emptiness, and wondering about it, and feeling something about it. The universe spent 13.8 billion years not being aware of itself. Then, in at least one location, and perhaps others we haven't found, matter organized itself into a form complex enough to become aware, to model the universe inside itself, to ask where it came from and what it's made of, and how long it will last. That awareness, your awareness right now reading these words or listening to this voice, is the rarest thing in the observable universe. Not because consciousness requires something outside of physics, but because the physics required to produce it is so specific, so demanding, so contingent on a long chain of exact conditions that the vast majority of space and time in this universe has never contained it, and likely never will. The emptiness is real. The 80% of the universe's volume that is void. The near vacuum of interstellar space. The almost nothingness inside every atom. The quantum vacuum's irreducible restlessness. The accelerating expansion that will eventually leave our local group alone in an otherwise empty cosmos. All of it real. All of it vast. All of it indifferent. And here you are anyway, something in all of it. A pattern of emptiness that knows it's empty and finds that worth thinking about. Let's end where we started. You're somewhere right now. A room, a bed, a specific configuration of matter on the surface of a specific planet. Above you, the atmosphere thins over about 60 miles into the near vacuum of low Earth orbit. Astronauts in the ISS are passing overhead right now, 6 or 7 of them, in a spacecraft about the size of a football field, orbiting at 17,500 miles per hour, living in a thin metal shell surrounded by the vacuum we've been talking about all evening. Beyond them, the Moon, 239,000 miles away. Beyond that, Mars, currently somewhere between 38 and 250 million miles from Earth, depending on where the two planets are in their orbits. Beyond that, the gas giants, each separated from the next by hundreds of millions of miles of near vacuum. Beyond them, the edge of the heliosphere, about 100 to 150 ATU from the Sun, where the solar wind ends and the interstellar medium begins. 5 spacecraft are moving through that region right now, the most distant things we have ever built. Beyond them, 4 light-years of near vacuum before the nearest star system. Then the Milky Way, 100,000 light-years across. Then 2.5 million light-years of intergalactic space before the nearest large galaxy. Then the cosmic web of filaments and supervoids stretching across hundreds of millions and billions of light-years, 80% of its volume containing almost nothing. And underneath all of it, at every scale from the largest supercluster to the smallest quark, the quantum vacuum, the irreducible restlessness of space itself. Fields that cannot be silenced, virtual particles flickering in and out at every point. You are sitting in the middle of all of that. You are made of it. Protons whose mass comes mostly from the energy of quantum vacuum inside them. Atoms whose volume is almost entirely empty. A body that does not touch anything it presses against. Only feels the repulsion of electron clouds separated by the true void between nuclei. And somehow, through no plan and no obligation and no guarantee, the matter that composes you organized itself over 13.8 billion years into something that can lie awake tonight and think about emptiness. That can feel something about the scale of it. That can find it both terrifying and beautiful in the same moment. The emptiness is not going anywhere. The voids will grow as the universe expands. The atoms that make you will spend the vast majority of their future, billions and trillions and 10 to the 100th years, as dispersed particles in a cooling void, no longer organized into anything like you. But right now, tonight, they are you, and you are here, thinking, feeling, aware, in all that nothing, something, that is not nothing. Sleep well. Good night.